Hello students, this is the second part of Unit 1 where we're going to have a look at the history behind atomic theory. So you can see we're going back really early in terms of the identification of particles. So back in 460 to 370 BC we had someone called Democritus, and even a little bit on from that, Epicurus. They postulated that matter consists of invisible, undividable particles, which they called atomos. Then we see around about the 1800s, we have two other scientists. You may have heard of John Dalton. I think you did when you did your first year chemistry. Matter consists of atoms that are homogeneous bodies that are perfectly alike, and he postulated the concept of atoms and molecules. We then had Avogadro, who spoke mostly about the behavior of gases. And if we go on a bit, we see that the periodic table, which I've already mentioned in the earlier part of this unit, Mendeleev and Mayer organized elements in order of their atomic weight, and they grouped elements together with similar properties. Okay, and then a whole bunch of scientists sort of had an awakening in the early 20th century, from about 1900 onwards, where we start to notice some amazing findings. So we have the scientist called Becquerel in 1896 discovered the radioactivity of uranium. J.J. Thomson figured out the charge of the electron. On the right hand side of the slide here you will see a picture of the scientist, and he actually won a Nobel Prize for Physics in 1906 for his work on the charge of the electron. The scientist Millikan, you've heard of the Millikan oil drop experiment. He determined the charge and the mass of the electron. In 1911 we have Rutherford, who you know about Rutherford's experiment, determining the nucleus. And then in 1913 Moseley was able to elucidate the nuclear charges by X-ray methods. And subsequently in 1885 a scientist by the name of Balmer discovered a visible line spectrum for hydrogen. And this is one of the practicals that you're going to do. You're actually going to determine and see the line spectrum of hydrogen, but we'll get to that in a little bit. And then in 1913, Niels Bohr developed his model of the atom that fit the Balmer line series for the hydrogen spectrum. So just to give you a bit of information, the table on the right hand side here, this one here, just sort of indicates the masses of an electron, of a proton, and a neutron, photons, neutrinos, positrons, alpha, beta, and gamma particles, and indicates the mass number, their charge, and even their spin. You should remember from first year your quantum numbers why we have a spin of a half, or even 1 or 0. Okay, go and refresh your memory on that information. Okay, so what happens with the hydrogen line spectrum? Well, what you're going to see in the lab is that for atoms and molecules, we don't observe a continuous spectrum. So like we see when we take white light and we pass it through a prism, you get the 7 different colors of the rainbow being evident. Okay, for a elemental spectrum, so in this case one for hydrogen, you have hydrogen gas inside a glass tube over here. Okay, it's a discharge tube, and what happens is that you will pass it through a slit, and once the light goes through a slit, it then goes through a prism, and once it goes through the prism, it then be able to split the information that you see. And what you see over here is 4 different lines. So you see a purple line, there's a purple line, a blue line, a green line, and an orange line. You'll actually see this in the lab. Okay, so this is the different lines that we get for hydrogen gas and their respective wavelengths. So the purple one appears at 410 nanometers, the blue line at 434, the green line, or blue-green, at 486 nanometers, and then the orange line at 656 nanometers. And if we looked at the total hydrogen line spectrum, you will see that we've got quite a range, and we talk about this particular area here that I'm highlighting is the visible spectrum for hydrogen, and that forms part of the Balmer series. Okay, you get the Lyman series, which is this series here, and you get the Paschen series and the Broglie series, which encompasses this section of the line spectrum over here. All right, so why do we see 4 lines? I mean, we assume it's hydrogen, it has 1 electron. What is this electron up to? Well, the movement of the electron in the atomic spaces is best described by some important classical mechanics. Okay, and you'll know from those of you who've done first year physics, you'll know that we can describe the change in energy as the value of Planck's constant times its frequency. We get the speed of light from this equation over here. We have the Rydberg constant that can be written in 2 forms, 1 in meters to the -1, 1 in centimeters to the -1. This one being, the bottom one here, being 1 in wave numbers. And we also have this equation over here, which will give us some indication of how to calculate the frequency as well as the wavelength. So you'll notice that I pointed out specific wavelengths earlier. This is how we would calculate them, and this is how you're going to calculate the various wavelengths of your lines for the hydrogen spectrum. Now, what happens? Well, this 1 electron can be very busy, and it can jump between energy levels. You'll remember from first year chemistry that we described the principal energy levels by the quantum number n, and you can see that the Balmer series, which is the visible line spectrum, shows a transition from n equals 2 to 3, n equals 2 to 4, and n equals 2 to 5. Okay, so you're going to get three of the lines coming from the Balmer series, and you're going to see the Lyman series, which is transition from N1 to N2, N1 to N3, and so on and so forth. Okay, so the hydrogen atom with its 1 electron, that little electron can be very busy in terms of moving around. Okay, so in 1903, the origin of energies was unknown until Niels Bohr's early form of quantum theory of the atom was predicted. It showed negative electrons in an atom move in a stable circular orbit around a positive nucleus with no absorption or emission of energy. Okay, electrons can absorb light of a specific energy and may be excited into orbits of higher energy, and the opposite is also possible. So this was his theory. Okay, now the problem is that his theory didn't work very well when you had atoms that had more than 1 electron, because that could not be described. And so there had to be a different way to postulate and describe this thing, and along comes a scientist by the name of Louis de Broglie, and he won a Nobel Prize in Physics in 1929, where he described that electrons can, even though they are particles, they can behave as if they have a wave type nature. And basically he stated that all moving particles have standing wave properties. So what you would see is something like this. Okay, so what you're visualizing here is a standing wave. So I want you to try and picture that a particle can move as if it were in a wave pattern. And obviously that means that the wave has a wavelength, and if it has a wavelength, then it has a corresponding frequency when we use Planck's constant and we use the energy values that you have learned about previously in physics. Okay, so the electrons in the Bohr atom behave like a standing wave with a specific wavelength. And there is the value of Planck's constant, and so you can determine the frequency of the wave. So something is going to look a little bit like this. Okay, so you'll find that if we have energy level 4, then we have maybe 4 standing waves. 5 is 5 standing waves. And we can't have fractional values in the energy levels because it would imply a mismatch in the waves themselves. Okay, so what does this mean? Is that if we're trying to determine the position of an electron, we're not going to be able to see exactly where it is. So what you're seeing now, the little animation on the screen, is you're going to see the movement of a electron in an orbital, and you can see that it causes a standing wave, but you can't necessarily find its exact position. You can only see the wave itself by the wavelength that is emitted from that particular energy level. Okay, so this then led to us not being able to accurately describe the motion of the electron, and you may remember Heisenberg's uncertainty principle, which simply states that if you know the position, then you will not be able to know the momentum, and if you know the momentum, you will not be able to know the position. I'll refer you back to some of the theory that you did in first year in this regard. Okay.